Good morning, Dr. S.
Sorry, good morning, Kyle and Arthine. I'm glad you're both here. Arthine, how are you doing today?
I'm feeling a lot better, thank you.
Oh, that's good. I read an article that, COVID is kind of coming back up despite the excellent vaccination rates in the Navajo Nation. So I hope all of you are staying safe and still using all those protective things that we have. So, well, we'll give it another minute or two here to see if people show up. Can I answer any questions for you as we get started? I know I saw Kyle, you jumped right into this work and I just looked at it. I didn't get it graded yet. I'll do that after class, but how did that go for you with the paired t-test? You're the first one to dive into it, I think.
Yeah, the practice, it went really good. I just did it right after the class, so my memory was fresh from the work that we did.
Oh, isn't that a good idea? Yeah, I think that's
it was helpful.
excellent. Yeah.
Because usually I wait until like Sunday or Saturday to do my work, but I just decided to do it that.
Oh, it makes it so much easier when it's fresh. And then as you reinforce it that way, then it stays easier too, because then you do all those repeated problems and it's less foreign the next time you sit down to it. So yeah, I'd really encourage you to use that route. Others of you, it's a really good idea. And the other thing, a student said this to me, that for her, it really made a difference to read the book. Like she, it surprised her because I don't think that's how she thought of herself as learning, but it really worked for her. And so I encourage you to do that too. And you're not even reading the whole chapter here. It's only about 4 pages or something like that. You're only reading the part relevant to the paired samples t-test. So it's not that bad. And I think your book makes things pretty easy. So in advance, I'm going to apologize to you because I still have this noise outside in my home with this work being done outside. So hopefully it won't disturb our class today. But I did record some more examples for you. And I want to show you what's up on our screen as we get started here. So I'm going to share a screen here for a moment. And so let me see which screen. I guess I'll share this screen. Just to show you what we have on our site, in case you're not sure of what the resources are that are available to you. You should be able to see the screen now. Can you let me know?
Yeah, I can see the screen.
Okay, and I should have gone somewhere else today. I thought they were done with this. Okay, so I just wanted to show you that we're still in this C unit. We are taking, this will be the last on this, but this is what's available to you. So this introduction to the t-test, this content is actually some example problems. And then I have also some bigger slides up here that I actually hope I have. So these are just some examples that I did that are more on using PowerPoint. So if that's a better learning mode for you, that might be helpful to you. And so then if you go into the next bit of content, you'll see that I just sort of teased apart what's different because there's really not that much difference. So here's our class meetings, and then these examples that might be helpful, the lecture, and then the whiteboard screens from our class. And then if you go on, you'll see that we have, I should just go back to there. Just a little, I've just teased out what the difference in the steps are for you. And I think I can turn this on and it'll be a little easier. So you can see what the difference in the steps are for you if you go in here. And so parsing the problem, I've kind of just described it to you. Your book does a nice job of this too. Then this big step, step 2, which is always the big step that changes. I did kind of review this process for you, and you'll always see it in the examples as well. And then steps 3, 4, and 5, essentially there's no change, but I do have the link here to that critical value calculator that I use in class, which is really helpful. It's easier than using the tables in the back of the book. And then what I have for you that wasn't quite all up when Kyle was doing this work, so I'm really glad that he went into it, is the assignment. But what I would like you to do this time is to do one problem at a time and then check the solution right away. Because if you do that, then you'll know right away, oh, I'm screwing up. And then you'll know to correct that before you go on to problem 2. So the practice problems, it's just 4 problems, and there's a demonstration for each. So you should have no difficulty with it. And actually, I made a video of the Excel solution as well, and I haven't linked it yet, it looks like. So I'll also post up that video. So, and then you can just go into the homework, which really is exactly the same thing as the practice. So you're really only working these, there are a total of 8 problems, that's it. And you have nice examples throughout, and then you have the quiz that highlights this. So that's what's available to you. And then I hope it's helpful. I keep trying to do as many things as I can to, give you access to this work. Then I'm going to just start today with just a few slides that I had prepared. So I'm going to share those at this time. And that is not it. Just 1 second here while I get those onto the proper screen. Okay. And I see a couple more joined us. So the students who joined us, I'm just going to repeat that one last statement that I offered about going through and doing the each practice problem one at a time. So that's what I'm encouraging you to do. So what I had just shown briefly to the students who are here is that when you do the practice assignment this week, please do each problem one at a time. So this is what it looks like. This is the practice assignment. Here's all the problems that you'll solve. But then I put the solutions here for them one at a time. If you look at the solutions ahead of time, you're just, I mean, I would have no way of knowing, but you'd be wasting your time. And I don't want you to waste your time because these practice problems are for you to learn how to do it for the homework problems. So if you do a problem and then look at the solution and check it right away, then you'll know right away if you're on the right track. And that's what that's what my goal is for you. So check the solution right after you do each problem and then find any mistakes you made. And then what I need to see is that you looked at the mistake and you said, oh, I see what I did here. I forgot to use the distribution of means. So you can do something like that. So let's continue on and get started. Here are the slides I was about to show you before. So I'm going to just pause for a moment here and be very quiet for an entire minute and see if you have any questions either in the chat or in the firsthand or in like live time. Okay. I think that was about a minute. All right, so we're doing this paired samples or dependent samples, and you'll see that I've used different names for it because there just are different names for this. So you'll see that, whoops, let's see here if I can get it to forward. You'll see that it's called the dependent samples t-test sometimes. I don't like to use that name. It's called the matched pairs t-test. It's called paired samples t-test, the repeated measures t-test, the t-test for dependent means, the t-test for related samples. They all mean the same thing. So what you can look at is like if you have data that are two sets of data, but they're related to each other, and I'll explain what this means in a minute, then you're going to be doing this paired samples t-test. So just to review where we were, we started out with the z-test where we had n equals 1. We reviewed this last time and we compared it to a population that had a known distribution, like a known mean and a known standard deviation. Then we had a sample that was n greater than 1, but we were comparing it to a population that had a known mean and a known standard deviation, and that was another z-test. But we had to then make sure we were comparing apples with apples, and we had to calculate the distribution of means. And that just meant that basically we took the standard deviation and divided it by the sample size. In a nutshell, that's what it was. We worked with the variance, as you know, and then went back to the standard deviation. Then we went to the one sample t-test that you did in chapter 7a, and we compared samples that were greater than 1 with a distribution that had an unknown, it had a known mean, but an unknown standard deviation or variance. And so then we had to change and use this t distribution. And so we had to look up the cutoff point. We had to go ahead and look up the cutoff point either in the back of the book or using that critical value calculator that I've shared with you. And then we also had to use the distribution of means. So we had to estimate the variance, and then we had to divide that variance by 5 to get the variance for the distribution of means. And now today, we're comparing a sample where n is greater than 1 with a related sample. And so the changes that the distribution that we're comparing is the difference of differences between those two scores. So here's what we're doing. Imagine, this is one example. We have matched pairs. So we have pairs of individual scores that we expect to be related. So if we're studying relationship satisfaction, like let's say we're asking husbands and wives, how satisfied they are with their relationship. Well, when we do the math, when we calculate out all the math, we don't want to just compare all the husbands as a group with all the wives as a group. We want to compare each husband with their own wife. And so that's why these pairs are matched, because we want to make sure that we're linking the data within each relationship. So that's one example. And I have example like that in your practice this week, I believe. I know I have it in your homework. Another way that we could have two related samples is we could have repeated measures. And what that means is that we have scores from a set of individuals, but we have two scores from each individual. We have a score that was taken before some sort of intervention, and another score that was taken after some sort of intervention. And if that's the case, it doesn't make sense to compare like my after score with Kyle's before score. We need to compare my after score with my before score. And so here, once again, we're going to subtract my before score from my after score. And that difference, the difference between my before and after score, is what we're going to use in our test. Once we figure out that difference, then that's what we work with in terms of calculating the mean. And an example here is we're studying the effects of an intervention that's going to help children with dyslexia learn to read. And we want to compare each of those students' scores after the intervention with that same student scores before the intervention. So these are the types of situations where we use this sort of test. And then sometimes there are natural pairs, like pairs of individuals that are related naturally, like if we're studying the trait of extroversion and we want to compare one member of a twin set with the corresponding identical twin. So we wouldn't want to compare a twin with someone else's twin sibling. We want to compare their scores with their own twin sibling. So these are the types of problems that we work with, and you'll see more examples as we go through them in class today. So are there any, so let me just jump back up to this first example of matched pairs. Matched pairs could be like husbands and wives, and that also might be sort of a natural pair, but sometimes we match pairs intentionally. Like if we have a classroom in statistics, a class, or let's just make it actually a high school math class, and the high school math teacher is doing some different type of teaching in one class, and then in the same teacher's other class, they're using an old style of teaching. And that might be, in this situation, the best way for this teacher to know whether the new style of teaching is worthwhile. But the two classes aren't exactly the same. So in that case, that teacher might match each student, match a student in class A with a student in class B. Like he might take the top student in class A using the old method and compare the scores of that student with a student in class B, the top student in class B. So in that case, the two top students would be a matched pair. And maybe he'd rank the whole class like that. The second top student would be matched with the second top student, and he'd match them all down the line so that each student's scores are compared with someone who's similar to them or who's matched with them intentionally in some way. So that's another way that matched pairs might be used. But all of these examples are the same because we're comparing the different scores between these two sets of scores. And so this is the first example we're going to work with, and we're going to go into the whiteboard and solve it by hand. And what the problems that I've given you this week are really short. They're like if I just had this bottom sentence, I tried to keep it that way in response to what someone commented on last week, that they were spending a lot of time parsing out the problem. And I thought, let's just keep these really simple till you get good at it. But here I just explained a little bit more about the scenario because this is psychology class too. So this is the idea that the school counselor had. There was a child, this is what his experience was. This is a real experience. There was a child who was being bullied. The child had maybe, I think, a mild bit of autism and maybe some other condition that made him a little bit different, and he was being picked on. And the mom was just really concerned about it because the boy was coming home upset each day. And so they, instead of like getting all kinds of kids in trouble for bullying, which sometimes makes them feel even angrier toward the victim, instead of doing that, they decided to find just a couple of the really popular kids, the kids who were like leading the bullying, and talk to them, but not get them in trouble. Instead of getting them in trouble, they decided to emphasize to them their role as leaders, like that they were the most popular kids in the school and that other people were doing what they did. And that as leaders, they could demonstrate their leadership ability by sort of standing up for this boy. And so this really happened. This mom told me about it. This effort really worked. When the top kids in school, just a couple of them, just one or two of them, decided that they were going to go along with this and start to be kind to this child, the bullying stopped. The bullying stopped. And so imagine that you were that counselor and you felt all this compassion for these kids who were being bullied. And you thought, wow, the way to deal with this isn't getting these kids in trouble. It's calling on the leaders of those groups and tapping into this innate kindness and to this sort of vanity they have as being leaders and getting them to defend the child. So you want to find out, could this work for more people, or was this just isolated? Did it work in only this one case? So this is the kind of situation that we decided to use. So this counselor decided he worked in 4 high schools, and he decided to go into each school and just start this effort that's called Leaders Lead. And that was just an effort to get the top kids who might be bullying other kids and get them to take leadership in the opposite direction. So we wanted to see, is this really working? Could this work as a more general intervention? So he got before scores, the number of incidents of bullying in the school each week, and after scores, after he did this Leaders Lead program. And so these are made up data. So I'm just doing this as an exercise, but this is the type of situation that it might be used in. And these are some made up data that we'll work through it with. So let me just ask if you have a good understanding of this problem. And could you please respond to me in the chat? If you don't want to speak up, I just want to know who's kind of with me here. So I'm going to just type in, you can speak, which is great, but thanks, Arthine. Thanks, Kiana. And whoops, it replied to just one. Let's see, who else do we have here? Sheridan, good. All right, so I see a few of you, and I hope it understands to all of you. And so this is the problem we're going to solve for our first example today. So what I'm going to do is copy out this very short version of the problem and put it onto our whiteboard. And then I'll copy the data, and we're going to start right from there. So I'm pulling the whiteboard up and grabbing the problem. So we're answering, does bullying decrease after popular school leaders are persuaded to defend the victims in 4 schools? And I'm going to actually do step 1 on the PowerPoint because it's easier to type sometimes than to write all that. My writing tends to get a little messy. So I'm going to just put the slide back up and solve it right there for the first part. And then we'll do the math on the whiteboard. All right, so here's the problem. And we won't look at the data just yet because let me just make that a little bigger. All right, so let's just do step one. Step one is always a little weird in these problems. I was tempted to just say, just write the hypothesis, but I just still want to make sure that you're understanding it. So I'm going to do the populations. So population one are the schools in which the leaders lead intervention took place. And then population two. So what are we comparing them to? So we're comparing the difference in scores before and after this effort in these 4 schools with a hypothetical population of schools with no intervention, with no leaders lead intervention, and thus no difference in measures before and after. So that's a little confusing, and I'm not going to be super, I'm not going to inspect this closely in terms of how you phrase it, because I think it's tricky. But we can easily do the same way the dependent variable and the hypotheses and the tails. So let me ask you then, what is being measured in this problem, or what's the dependent variable? And type it in, please. Thanks, Kyle. Others? Dependent variable, our theme, good. Let's get maybe a couple, two or three, at least a couple more answers. So the question I'll type, what is the DV, the dependent variable? Whoops. I'm always typing this to one individual accidentally. Anyone else? Thanks then. Good. It is bullying. It's the number, what they're actually counting are the number of bullying incidents. I just put in a week. That's, or maybe it's a month would be a better estimate. I just made these up, as you know. Okay, next we have the tails. Are we looking for an increase or a decrease in bullying? One tail, are we going with one tail or two tailed? Type in your answer, please. I'll type the question to you. Thanks, Shanielle, our theme. Good. Good. So we have a couple more. Anyone else have some thoughts on this? Our theme. You said one-tailed low, and you're correct. How did you know that?
Because of the word decrease. Right.
Because of the word decrease. So you caught sight of this word, you know right away that this researcher hypothesized a direction that the bullying is going to go down. And so you knew you were doing a one-tailed test and that you were going to be looking for a value in the lower tail of the distribution. All right, so the tails is indeed one-tailed low, and then we'll write up the hypotheses. So in this case, we're going to state that what we're looking at comparing are change scores. So the hypothesis, the research hypothesis will simply be that the mean difference, so let's see if I can get a mu here. Nope, I don't have that set up in here. Let me try. No difference. Okay, so I'm just going to write the mean difference in bullying before and after the intervention will be, well, the difference is going to be lower for population 1 than for population 2. And I'm gonna, when we go into the whiteboard, I'm gonna write this in shorthand because I think it's easier in this example. And the null hypothesis is the mean difference in bullying at the before time point and the after time point will not be lower. And there is no intervention. Before and after will not be lower. That's why this is a little confusing in here, and that's why I sometimes go right into the shorthand just for this test, because it's just a weird kind of a phrasing. So let's go now into the whiteboard. So the problem is here. I'll just paste that in for us again. I believe we're directed to use, whoops, paste it in. Enlarge it. All right, here's our whiteboard. And it's quite large, so let's shrink it down a little bit. And we were directed to use 0.05 for our p-value. And so this will guide us in this problem. Okay, and let's put our data in here too then, and then we'll start with the data. So this is what we have to work with. So we have the incidence of bullying per week, and we have the before and after scores. And I actually think that I'm going to get rid of that heading because we know what we're counting here, and that'll be a little easier to work with. All right, so we have these 4 high schools. So these are our scores. So let's start out just by writing those hypotheses over again. So what I'm going to do is I'm going to write the steps on the left, and we'll do the calculations on the right. So in step 1, all I'm going to write are the hypotheses. So here I'm going to just head it steps. This is so we can organize the work so it's a little easier to read. So step 1, all I'm going to write now, since we did this work earlier, are the hypotheses. I'm going to write it in shorthand. Hypothesis 1. The mean difference for population 1 will be lower than the mean difference for population 2. And the null hypothesis is going to be that the mean difference for population 1, we can either write will be equal to, is what's typically written, the mean difference for population 2, or you could write the less than sign and cross it off, and either would be okay. In step 2, I think I'm going to change colors as I go through these steps here, so it's a little easier to see. So in step 2, this is the step where we need to describe the comparison distribution, and usually this is the most challenging step. So we're going to describe the comparison distribution. What are we comparing these people who had the interventions to? What are the characteristics? What are we comparing them to? And in this case, we describe it in the typical way. We describe the center. We describe the shape. And we describe the spread. Always in this type of problem, when we are looking at the center, it's going to be 0. Now we have an airplane, sorry. Guess I live in a noisy place here today. Can't wait to get back up north and just tomorrow where it's quieter. Okay, so the mean difference equals 0. And the reason for this, so I'm going to put notes in orange here. This is because we expect that schools that had no intervention would have no change, no difference before and after, and that no difference is represented by 0. So I'll write a little note here that says, I'll write it really little. We expect that schools without intervention would have no change in bullying. Why would they have a change? That's what we're comparing it with, schools with no change. So that's why the 0, but it's always going to be 0. So anytime you're asked for the center of the comparison distribution, it's going to be 0. The shape of the comparison distribution is going to be the t distribution, and it's going to be normal in terms of its general shape. And it's going to have, I'm going to give myself a little more space here. And it's going to have the shape of the normal t distribution will be the shape that's given for degrees of freedom. And in this case, we'll write this out in a moment. We'll indicate this in just a moment. And then the spread is going to be the estimated standard deviation for the distribution of means. And so we'll fill this in a moment too. So this is what we're going to need for our shape, and we'll write it out this way. And I just added that note for your benefit. And so I'll draw the picture, or I'll draw the illustration in the end. So now let's do some of our calculations. Let's first get our basic information. I'll just write basics here. And our basic information is going to include the n. In this case, we can see it equals 4. There are 4 schools. The degrees of freedom, which you know already is just n minus 1, so it's going to be 3. And we need the population mean, which is given right here, and we know it's always going to be 0, but let's write it down just so we are consistent. And then we're going to need the mean difference scores, and I'll put this in a new line. And we're going to calculate these out. Now, in the past, we would have, say, calculated the scores, the mean difference for, say, one set of scores, but now we have 2 sets of scores, so we have to calculate the difference. So we calculate the difference, and let's put, now we're going to get a score for each individual, which will be named X. That represents the score for each individual, but it's going to be the difference between their before and after scores. And so we're going to calculate it, and we're going to calculate it, here I'll put a note, by going after, taking their after score and subtracting their before score. And so let's go ahead and do those calculations. So 15 minus 35 equals negative 20. 4 minus 22 equals negative 18. 9 minus 17 equals negative 8. 12 minus 28 equals negative 16. Sorry for all the negatives. The reason all these numbers are negative is because these are the numbers of bullying incidents, and they decreased. So they went down by 20 at Tau High. There were 18 fewer incidents at Sunnyside High. At Baker High, there were 8 fewer incidents, and at Abel High, there were 16 fewer. That's why all these numbers are negative. So this is the data we're going to work with, and we are done with these data. Right here in this difference score column, it's as if we're starting a 1 sample t-test using these data right here. And so that's how you treat it. You have to do every single step after this. You've just eliminated this as if it's not here, and these are the scores we're working with. So now we calculate the mean difference scores, which is just the sum of all those scores that we just figured out, the sum of all those difference scores divided by n. And if we do this, we find that we just have minus 20 plus minus 18. I'm just going to do this as an example. 8 plus minus 16, and that gives us, oh, I didn't sum it separately. Let me just do a separate sum in my spreadsheet here. So the sum of that is minus 62 divided by 4. And so that's how we calculate out the mean in that. And that gives us a mean of minus 15.5. All right. So first off, we know now that we can fill in the degrees of freedom. The degrees of freedom is 3. So we know
Do
that's
we
going to be
add
the
those
same.
numbers or do we subtract?
To calculate the mean.
Yeah.
Well, the sum always means you add them together, but if you add negative numbers together, you get a larger negative number.
Yeah.
Yeah, so that's why I should have found a problem where we're working with positive numbers. I didn't want to see an increase in bullying, so I should have thought of a different example. But that's just a fluke. You're going to add them together. You're calculating the mean just like you calculate a mean in any other situation. You sum up the values and divide by 4. Because we're working with negative numbers, then we have a negative mean. So how does this first step go? This is the only step that's different than from your homework in 7A. This is, in a nutshell, this is the only difference between the one sample t-test and the paired samples t-test. So now that we have this row, everything we do is going to be the same. Questions on this? Okay. If you have them as you come along, just ask them. So next thing that we have to do is we have to calculate out this standard deviation for the distribution of means. And so we're going to start to do that now. And so let's go ahead and write down the 2 steps that we have to have. So we're figuring out the standard deviation. So I'll write step 2. Because these are the calculations for step 2. And now, and so we are determining spread. We have the other info down already. So we do that in 2 steps. It is possible to do one single formula and get this all done, but that does not help you understand why you're doing what you're doing. And so you'll forget. And so we do it in 2 steps. The first step we do is we estimate the variance. And that is for n equals 1. All right, so that's the first step. Of course, we know that's not going to be the final step because we don't have n equals 1, we have n equals 4. So let's go ahead, let's work on step 2 here. And we estimate the variance calculating the standard deviation the same as we've done from the start of the term with just that one small difference. So the first thing the 2 pieces of information we're going to need is we're going to need the sum of squares. And we're going to need the variance. So the sum of squares means the sum of squared deviations. So let's go ahead and figure out the deviations. The deviations is just the difference of each score from the mean. I always forget I like to put the mean in here. So we're going to calculate out I'm just going to fill in the mean difference. Let me just use a color here to show that we're not calculating. This is the mean difference, and I'm just going to transfer it in here. I'm just going to write it down from what we've already done so that we can do the math easily. The mean difference is this right here, 15.5 minus 15.5 minus 15.5 minus 15.5 minus 15.5. So this is what we're doing for our next step. We're going to take all these different scores and subtract the mean difference. And that will give us the deviation. In other words, it's telling us how far is each of these mean differences from the center. How far are each of these scores from the mean? And so minus 20 minus 15 point, subtracting 15.5 is minus 15. Hang on just one second. I have an error in I have an incorrect reference. I have an incorrect reference in what I was doing, so let me just correct it. There we go. All right, now I have the correct reference. So the first one, minus 20, subtracting minus 15.5 equals minus 4.5. The next one is minus 2.5. Next, we have minus 7.5 and minus 0.5. So these are all the deviations. They're all negative numbers because we're still working with this decrease from earlier, the decrease in bullying. And so, in other words, this first score for Tau High is 4.5 bullying incidents away from the mean. The score for Able High, they had a decrease of 16 incidents. Well, that's really close to the mean. It's only 1/2 of a bullying incident away from the mean. So those are the deviations. What we're looking for in the sum of squared are the squared deviations. So let's go ahead and get our deviations squared. We multiply each one times itself. And for the first example, we get 20.25. Does everyone know where that 20.25 came from? All I did is subtract, is square this 4.5. 4.5 times 4.5. Let me put a note up here. It's just 4.5, negative 4.5 times negative 4.5. That's what we mean when we square something. Next, we have 6.25. We know that if we multiply two negative numbers together, we get a positive number. So that's why minus 2.5 times minus 2.5 equals 6.25. Next, we get 56.25. And finally, 0.25. We are now done with everything we're doing up here with the data. We're finished. Now we can fill in everything else we need down here. The sum of the squares is just the sum of all the deviations squared. And that equals 20.25 plus 6.25 plus 56.25 plus 0.25, which equals 83. We get the variance then. Remember, this is variance. It's just it's a code. S squared is a code for the estimated variance. The variance is just the sum of squares divided by degrees of freedom. And I'm going to write a note here. We use degrees of freedom because we are estimating. That is how we make an estimate. We're saying we're not going to get a perfect answer. And so we're going to divide by this number that's a little less than the correct n in order to just have a number that's a little more cautious. That's what that's about. So the first thing we did was we estimated the variance. So now we know the variance for the population of n equals 1. But the second thing we have to do is we have to realize we have n equals 4. So we have to calculate the distribution of means. We have to calculate the standard deviation for the distribution of means. Recognizing that we have 5 in our sample. So we have to compare it with samples of 5. And we simply do that by first calculating the variance for the distribution of means, and then calculating the standard deviation for the distribution of means. And so this S squared M, all it means is variance for the distribution of means. We use the S because we've done an estimated variance. And we just take the variance for the group of individuals and divide by n, that's it. And in that case, that equals, oh, I didn't finish writing that out. So let me just write this right here. SS divided by DF in this case equals 27.66667. So I'm going to have to erase my little note here. 27.66667. And so now we take this variance, 27.66667, and we divide by 4. We no longer have to use degrees of freedom. We're done using that. We already estimated. We know that the standard deviation for the distribution of means is just the square root of the variance for the distribution of means. And in this case, I still have to calculate this out. 6.916. Where am I? 67. And so now I have to take that 6.91667 and figure out the square root. And the square root, as you know, is just the number that if you multiplied it by itself, it would equal this 6.9. And in that case, that number is 2.629956. And I'm writing it all out because we're using it for calculations here. But now I'm going to take and write it up here in its shortened form. And so it equals 2.63. And that's what we'll use when we report the standard deviation for the distribution of means. That's the biggest step, people. After this, we're going all downhill. So what questions do you have about this step that seemed like it took such a long time?
For the estimate variance part, I thought we divided by 83.
So 83 was the sum of squares. So we just summed the square deviation. So our sum of squares we got by summing all this row of squared deviations, right?
Mm-hmm.
And we used that to calculate the variance. We took that sum of squares and divided by degrees of freedom. And then now we're done with that. So now we take this number that is our variance and we just figure out what is the variance for the distribution of means dividing by 4. So we don't ever divide by the sum of squares. We always take the sum of squares and divide by the degrees of freedom. What that gives us is like the average variance.
Calculation, I got 83.25. So we don't do the after, like the 0.25?
Could you say that one more time?
For my calculations, I got 83.25.
It comes up to me for 83, but let me see if I erred in one of my calculations. So taking the sum of squares, I took the sum of 20.25 plus 6.25 plus 56.25 plus 0.25, and it comes up to an even 83. And I know that makes sense because I know that if we just take the 0.25 plus 0.25, like these are quarters, right? 0.25 plus
Yeah, I got
0.25.
83.25.
Yeah. So you must have missed a 0.25 in there somewhere. Or you
Okay.
must have added an extra one or something, because we know that if we have 4 quarters, we get $1. I know that I'm going to have
Okay.
no decimal
Okay.
places at the end.
All right.
But I'm really glad you're working through this with us because it helps you identify if you make any problems, any errors. So when you're doing this, I suggest you just walk through it right with me.
I guess for the 20.5, I put 20.50, not 20 0.25, sorry.
Okay. Oh, that's good. Then you caught your error. You see, this is
Yeah.
why we do this. Now, this is exactly what you should do when you catch an error. You can say, why did I get 83.25 and she got 83? Then you walk backwards. And what you just did, Kyle, is exactly what you should do. You should go backwards and you discovered, oh, I just wrote this number down wrong. An easily
Okay.
corrected error that shows conceptual understanding and a little transcription error, which is why we use Excel. And I'm going to show this to you when we're done with it. Okay. And you don't make those errors in Excel. All right, so let's just go on and finish out this problem. We're just about done with it, even though we're only on step 2. Step 2 is the doozy. So let's go to step 3. We find the cutoff point, easy peasy. We have that nice calculator I showed you. We just have to go and know what our p-value is, and our p-value was indicated at 0.05. So let's pull up our handy calculator. Oh, I don't have it open. I always have it bookmarked for myself. Find a good one and just hang on to it. So here it is. Whoops. There it is. So here's 0.05. We'll change the p-value to 0.05 because that's what we're looking for. We'll change the degrees of freedom to 3 because that's what we have, and we'll hit calculate. We know we're doing a one-tailed low test. Please type in, looking at what we have in front of us, what is our cutoff point for a one-tailed low test with 3 degrees of freedom at 0.05? I'm going to type the question out. Thanks, Kiana. You are correct. Let's hear a couple more people.
Negative 2.35.
Yes, yes, indeed. All right. You guys are on top of it, those of you who responded, and I think the rest of you probably are too. So let's get this problem done with. So our cutoff is negative 2.35. Let's draw this out for ourselves. It's always helpful to draw it. So here, let's see, where should I put our little, I'll do this at the end, I'll do the drawing. Our next step is to calculate the t-score. Some people forgot this step, but remember, we're always comparing a t-score, which is sort of like a z-score, a standardized score. So we're going to calculate the t-score. And t just equals the mean for the sample minus the mean for the population. So the mean, we know that we're working with the different scores, the sample mean minus the population mean divided by the standard deviation for the distribution of means. In this case, it's easy peasy because what is our population mean? Our population mean is 0. So we don't even have to do that subtraction. So we just take our mean difference, which is way up here. Remember, we calculated this right at the start, our mean difference scores. That's what we've been working with. So negative 15.5 minus 0. So it's really just negative 15.5 divided by this number, this 2.62. I have to write it all out because we're calculating with it, 2995. And that equals a t-score of, oh my, minus 5.89. I'm just going to write it that way because we don't need to report it any more precisely here. We're not using it. And so let's draw this out and make our decision and draw our conclusion. So in this case, just so we're clear on what we're doing, we're comparing our sample score, a t-score of minus 5.89 with a distribution where there's no change from before to after. It has a mean of 0. So here are our t-scores in any case that always have a mean of 0. The 1's going to be about here, the 2 standard deviation here, minus 1, minus 2. We were doing a one-tailed low, so we are looking for a value that is resting somewhere in this tail. And we had a cutoff point of minus 2.35, so right about here, minus 2.35. And let me just shade that in. So any score that fell in this shaded region would yield a significant test result. We had a score of actually minus 5.89, so really big. So here's our minus 3, minus 4, minus 5. We're almost to minus 6. So our sample score was right about here, well into the shaded region, far to the extreme of the cutoff point. So what do we conclude? Type it into the chat, please. What do we conclude when our score, our sample score shows up like this? Or what do we decide, I should say? I'm typing that in. This is a really critical part of the understanding here, is to know what decision to make.
Is it a reject hypothesis?
We are, yeah, our theme, Kyle, absolutely, we reject it. Our sample is really well outside of what we would expect by chance. Our sample t-score was minus almost 6 standard deviations below the mean. Remember, all of the, so 95% of the values of sample size 5, 95% of the values are going to fall in here. Only 5% of the values are going to fall in this tail. And look at, to have a value that much lower, that is really a huge difference. So we definitely, Kyle, our theme, you were correct. We're definitely going to reject HO. And we're going to conclude that schools implementing the leaders lead program experienced a significant decrease in bullying. And then we put our statistic, T, we're going to write the t-score, but we always put in our degrees of freedom so that the individuals know. And our t-score was minus 5.89, and that was well below, the probability of getting that was well below our cutoff point of 5%. And so that's how we would write our conclusion. Always make sure and include the statistic. So that's the problem. Now, I would like to go through this very same problem in Excel, because that little mistake that Kyle made in transcribing, you just don't, you won't make those mistakes when you're doing it this way. So what I'm going to do is get our data up, and I'm going to share my Excel screen. And let me get a new page up here. And so here is the basic problem coming up. And I'm actually, I took the time to make sure these looked right in Excel. So I'm going to get the headings that I used to make it look right. And then I'll show you how simple these are in Excel. Okay, so this is sort of how we've laid out this problem. Now let's just watch how we would do this. So first off, I'm not going to rewrite out the, can I get this to come? I'm not going to rewrite the hypothesis in step 1 here, but let's just get the information down, the calculations. We know that the mean, oh, I didn't do it there. Let me see if I have it anywhere. We know that the population mean is always going to be 0. We know that the mean difference scores are going to be the average of differences that we have to calculate. So let's go ahead and calculate the difference scores. So I think I have this written down somewhere. Okay, here we go. So each score, the X stands for score, difference stands for the difference. So we're just going to type an equal sign. And we're subtracting the before score from the after. So I'm going to click the after score right here, D6, you'll see that up here, and subtract. So I hit minus, and then the before score. So that's what it's going to do for us. I'll hit enter. It looks correct. It came up with the same data that we had before, minus 20. And so now we're going to just copy that formula and paste it down so we don't have to solve all these individually. And it will do that for us. We just select the rest of the range and there it is. Now we have our scores and now we can calculate the average. The average here is really easy. In fact, there's even an easier way to do it. The mean is the same of average, and in Excel, we could just type equals, tell it we're doing a formula, and let's just type out average, A-V-E-R-A-G-E. Type the opening parenthesis to tell it what we want the average of. Let's select those 4 cells and close it. Now we have the mean difference is 15.5. What I do next is I always want to fill in that mean so I can have it up here and do a nice easy formula. So I'm just going to type it in. There are other ways to do it, but for this example, whoops, I'm just going to type it in. We don't even need the equals sign. I just put it there by accident. And now I'm going to paste it down to those cells. I don't have to do all that hand stuff. Now we know the mean difference is written there. And so now we have to, so we're done with this stuff. We used this already for our calculations. So I'm going to just kind of gray it out a little bit so we remember we're done with it. This is what we're working with now, these mean difference scores. We know that our N is 4. We know that our degrees of freedom is 3. There's all the information that we need for our basics. Now we have to estimate the we estimate the variance. You'll remember that we had to do that by first calculating the sum of squared deviations, and then we estimate the variance by dividing by degrees of freedom. So I do that up here really easily too. So let's calculate the deviations. All it is equals, let's take this mean difference, the score, each individual score, minus m, x minus m, the same as it was all along, equals x minus m. There's our deviation. I feel like I did something wrong here. I'm not seeing what it is. What did I do wrong here, people? Oh, I forgot the negative sign. By the way, I love it when you guys correct me when I make a mistake. It's the best thing ever. So here I have to get that negative sign in here. That's what I did wrong. That looks better. It's always the mistake I made. Now I can just copy this formula. So now we have this is correct, minus 4.5. Minus 4.5. Now I can copy this formula. If I just click on the cell, I can copy it. I see that line, that means it's copied. I select the cells I want to paste it and I paste it. And so now we have all those deviations. Now we have to do the deviations squared. And so I can just take equals, and I can just take this cell, this times this. And I can copy it and paste it down. Now, sum of squared deviations is just the sum of these values. So I can just go ahead and calculate equals the sum. What do I want to sum? I want to sum the squared deviations. So I'll highlight those cells, hit enter, 83. There's that 83 we were working with. I know the variance is the same as sum of squares divided by degrees of freedom. And so I can just type equals. I can click on the sum of squares and divide by the degrees of freedom. There's that 27.6667 we were working with. Now that is the variance for the distribution, the variance for n equals 1. Now we need to deal with the fact that we're using sample sizes 4. So we have to take and calculate our variance for the distribution of means, which is just equal to this variance that we just estimated divided by n. And there's that formula. And now I can do the very last step, which is to get it down to the standard deviation for the distribution of means, which equals the square root of the variance for the distribution of means. Enter, there we are. Now we're all done with step 2. Now we can look up the cutoff point. We already found out that was minus 2.35. I'll write it in there though. That's okay. And now I can calculate the t-score, which we know is just the sample mean minus the population mean divided by the standard deviation for the distribution of means. So we'll go equals, where's our sample mean? Here it is. Minus our population mean. Here it is. And let's go ahead and take that number and divide by the standard deviation for the distribution of means. Let's go equals, let's get this mean difference, and let's divide by the standard deviation for the distribution of means, which is right here. And there is that same t-score. So now all I have to do is compare this t-score with this cutoff point. I can see that this is more extreme than the cutoff point. I can decide to reject the null hypothesis because the sample t-score is more extreme or further into the tail. The cutoff point. So I really encourage you to try this. You won't make those calculation errors. You won't have to write down these big numbers and type those into a calculator. This really is the way to go. You'll be richer if you can learn to feel comfortable with this.
That seems like a lot.
Okay, well, how about if we just do it really, how about if we just
I
do
think
it?
I'll stick to the paper. I'll just relook at the numbers.
Oh gosh, Kyle, let me do an example and just show how, oh, I really want you to see how easy it is. All right, let me give you another example. Let's get a really big example and you'll see why to use Excel. So let's get this last example right here. Oh no, our time is almost up. I'm going to show you this example and I'm going to do it so fast. So Kyle, imagine that this is your situation. You have, here we go. Here's the question. We're going to look at, do mothers and sons differ in their estimates of how many hours per week teens spend on video games? So we're looking at mothers and sons both taking an estimate of how many hours per week they spend on video games. So in this case, pair one, the son estimated 15 hours and the mother said 20. Pair two, they both estimated 21. Pair three, the son estimated 3 hours and the mother estimated 26 hours. So you see these data. Now imagine, Kyle, that you have to do this whole process for this group. Now watch how I bet you I can do this before our class time is over. It's not that hard. First off, I know that I need difference scores. So let's just calculate the mean difference. So let's just calculate the difference. I'm going to just write XDIF. I'm not going to worry about making it pretty. The mean difference is just equals, and I'll take the mother. Actually, I'm going to go with the son score minus the mother score. It really doesn't matter, but then we'll have positive numbers. So there we go. I've done the calculation. Now, imagine yourself, Kyle, writing all of this out. Now watch how I can do it. Just zooming down the page here and pasting. Now I've got all of those scores. Now, I know that N is 20. I know that DF is 19. I know that the mean, the sample mean is what? I don't know yet, but let's calculate it. Equals the average of all of these scores. And there we go, minus 12.25. Now, I know that I'm going to need to paste this mean up here. So I'm going to put the mean here, the mean difference, and I'm going to paste it. Hang on a second. It was minus 12.25 is the mean difference. All right. So here we go. I'm going to just paste it all the way down. So now we know the mean difference is pasted in there. I have to calculate out, I know the deviations. We're all done with this son mother stuff, so I'll just dull it for us so that we remember we're done with it. Here's the difference, the mean difference. So now we calculate the deviations for this big data set. Here's our deviation formula. And I know I'm going to want to square the deviations. So I'm going to go ahead and do this for the first one. I'm going to just type equals the deviation squared. Now I have the formulas right. I'm going to copy both of those and run it straight down the page, all the way down. That's done. Now I know I'm going to need the sum of squares to estimate the variance. So I can go equals and sum up all these squares, squared deviations. And whoops, I missed my formula. So let me undo that and do it again. Equals the sum of all of these. That's done. I know that to get the variance, I'll just write variance there, the estimated variance. I have to take that sum and divide by degrees of freedom. Now that's done. Now that is the estimated variance. Now I have to calculate the distribution of means. And I just do that by taking the variance. So the variance for the distribution of means is just the variance divided by n. That's done. Now the standard deviation for the distribution of means is just the square root of the variance for the distribution of means. That's done. Now I calculate the t-score. That equals just the mean, sample mean, minus 0. So I don't need to do anything, divided by the standard deviation for the distribution of means. The t-score is minus 4.51. The cutoff point is, we have to look up, let's get out our calculator. The cutoff point, let's test at, what did it say, the test at 0.01 or 0.05? Let me just take a peek. It said to test at 0.05. So let's go ahead and do that. 0.05 degrees of freedom is 19. We'll calculate. And we were looking for a two-tailed, so we're looking for plus or minus 2.09. Plus or minus 2.09. And so if we compare, we know right away that this minus 4.51 is going to be beyond minus 2.09. So I know that my decision has to be to reject HO and conclude that mothers, there is a significant difference between estimates of time spent on video games between mothers and sons. So I guess, and then I could put the statistics. So if you now imagine yourself having to calculate each one of these. This is why it's beneficial to use Excel. It's only a very rare situation where we have a t-test with n equals 4. So just keep this in mind as you're working through these. You save yourself a lot of time if you learn to get comfortable doing these in Excel. I know you don't know the formulas yet, but they're really easy to learn if you just give it a try. So I would encourage you to keep giving some effort to this, Kyle. Even though I understand your comfort with working by hand, you really will have a better tool if you learn to use Excel.
No promises. Just kidding.
Give it a try. And yeah, I would encourage you, but it's up to you. So thank you, everyone. What questions can I answer? And then if anyone wants to stay around for some individual help, please do that. Otherwise, can I answer any questions before we sign off? Everybody, thank you for coming. We'll start the t-test for independent samples next week.
All right, see you, Dr. S. Thank
Bye,
you.
Kyle.
See you.
Bye, everybody. Stay around if you have questions. Yolanda, can you stay around a minute? Yolanda, can you stay around a minute, please? Yolanda?
Oh, Professor, I just
Yes.
had a quick question about this doesn't pertain class, but
Okay.
it's more just about the like an advisor.
Yes.
Yeah. I just wanted maybe I could email you about it. Because
Of
I know
course.
that the advisor I had, she said that she no longer is my advisor, so I was trying to like
Yes.
reach
It's
out
a,
to somebody
yes,
else.
I'd be happy to work with you. We are now trying to reassign all the students. We lost our wonderful Tara Lamott, who was doing much of the advising for us. So I need to, yeah, I would be happy to work with you. I don't have access to your transcript, so I would be best able to work with you if you could bring your transcript.
Okay, then. Okay.
Or you could work with Dr. Bradway or Dr. Barber or Dr. Bigot, any of them you're okay working with, and you just need to contact one of them. We haven't finished reassigning yet. This happened mid-semester and we're working on it.
Yeah, it was kind of like it kind of threw me off a little because I was like keeping in contact with her and stuff. But yeah, so I would just send you my transcript or more just message Dr. Bradway or one of those guys.
Whoever
Just
you
to be
felt
free.
like it, Dr.
Mhm.
Bradway right now has access to that material. Next time around, probably in about a week, I'll have access as well. And I'm not sure about Dr. Barber or anyone else. So you could contact, I'd say work at this time with Dr. Bradway, who has the best access right now. But otherwise, if you bring your transcript, I don't think that access really matters. So you can meet with anyone as long as you have your transcript.
Okay, then that sounds good. Thank you
Yeah.
so much.
Thanks for asking. I'll make an announcement about that sometime soon.
Okay.
All right, thanks.
Have a
Bye-bye.
good day.
You too. Okay, Kyle, I see a question from you. I'll have to email you because I have to run a calculation in order to get it. But I think you're doing just fine, but I'll let you know what your grade is. Okay. And let's see, Yolanda, are you here? I need to talk to you. Okay, Yolanda, I have a brake problem on my car and I didn't get back up north. And so they're working on it today, but I will not be in town tomorrow at 2. Can you meet with me next Tuesday after class? I'm going to be leaving Friday morning, but I won't get up there in time for the meeting. Can you meet with me Tuesday after class?
This is Yolanda. Yes, I
Okay.
will, and I need to meet with you. Yes, I feel that it's important that I do.
I would like you to, if it's
Tuesday,
possible.
I'll be there, and I did get your information announcement on the class announcement.
Okay. And so if you want to, I just need to see more work from you. So if you want to, if you could just like kind of like just do your work there with me there maybe, or plan to be there for a little bit. And maybe if you could just devote some time, you could just do it right there and get these submitted. And we could even, I'd need to go back to, we could do it at my place if that would be okay with you, because I have this puppy to tend, but we'll stay in the classroom. And then if we need to go longer, we'll go back to my place and you can finish or whatever you need. Because I just need to see that you understand all this stuff, okay?
Okay, I have some work. I just want to sit down with you and show you what I did, and
sure.
And I just need some help from you.
Yeah, excellent. All right, then I'm really glad I got in touch with you. I didn't think I had a phone number for you. I was trying to call you yesterday and So I was really feeling worried that you might do that drive tomorrow and I wouldn't be there. So I'm glad I talked to you.
Okay. I'll see you
then.
next Tuesday.
Sounds good.
Have a good day.
Drive
Bye.
safely. Bye-bye.